Yesterday, at some point, I realized that, as the first speaker of the conference, I should probably say something special to thank properly you and all the other organizers for the effort you made in order to make this gathering possible, even though online. But I also realized that I'm definitely not very good at it. So what I'm going to do is just simply say thank you, to the organizers, for this amazing event that you organize every year. And I'm leaving to the other speakers to find something more elegant and more clever, a nicer way to thank you. And I'm moving directly to maths, talking about my research, which, as the title here says, is basically a weighted investigation of the one-level density in certain families of L function. So the setting is quite classical because the notations are basically the same as in the case of the density conjecture. So everything starts by taking F, curly F if you want, a family of L functions in the Hilbert class, let's say, with symmetry type G. And with that, I mean that from Katz-Sarnak philosophy, we know that all natural enough families of L functions, at least for many purposes, can be understood, can be studied, just by looking at the group of the classical compact group of matrices, which in some way identifies the behavior of the family, which governs the behavior of the family. And this is going to be typically unitary, symplectic, or orthogonal. So that's what I mean when I say we take F with symmetry type G. So we consider the family F with attached these compact groups, this compact group which governs the behavior of the family. Then we want safe conditions. So for all the L functions in the family, we assume the Riemann hypothesis so that all the non-trivial zeros of the L functions elegantly line up on the critical line. And then we consider small f as a test function. You can think of f just as a characteristic function of the interval 0, 1. Actually, in reality, it's a smooth version of this characteristic function, but it's okay. And so what's the quantity then Katz-Sarnak studied? Basically, they consider the following quantity. So they took the test function f, evaluated at the imaginary part of a non-trivial zeros of one of the L functions in the family, and they normalized by dividing by the mean spacing of the non-trivial zeros. This is a quite classical normalization. Then they sum over all the non-trivial zeros of the L function L, which is for now fixed. So this quantity is basically a smooth localization of the counting function of non-trivial zeros at the central point. That's why it's a bloody difficult quantity to study, because it smells like pointwise analysis, almost pointwise analysis of the non-trivial zeros of an L function. So that's a problem we want to avoid. So what people usually do to make things easier, doable, is to add an external average over the family. So we also sum, and that's what Katz-Sarnak did, we also sum on over L, which varies on over the family we are considering. We normalize by, of course, the cardinality of the family, and then the conjecture that Katz-Sarnak proposed is that this quantity here, if the family is large enough, behaves as follows. So in the limited, that's given by the integral of the test function of the reals times a function times a kernel, which does not depend on the family we're working with. Or I mean, it does depend on the family, but only through the symmetry type of the family, not on the specific family we're working with. So this conjecture here, this expression that I've written, is saying that the left-hand side, which is a quantity which is all about the low line zeros of the DL functions in the families, because only the zeros which are close to the central point contribute in this sum by definition of F, basically. This low line zeros distribution only depends on the symmetry type of the family and not the specific family we're working with. That's the key point, the key idea behind the density conjecture. And so since the particular family we're working with is not the main point here, actually, in the following, I'm focusing on 3 specific families, one for each symmetry type. So a unitary family, a symplectic one, and an orthogonal one. And in particular, in the unitary case, I'm considering probably the most natural one. So the family of the Riemann zeta function, that's a continuous family parameterized by a vertical shift. For example, the density conjecture, which has, of course, not been proved in full generality, has been proved at least if F is good enough, let's say, in the unitary case, so for this specific family. Also in the symplectic case, I'm considering probably the easiest case, the easiest family, which is the family of quadratic Dirichlet functions. And then finally, if we take a modular form and we consider the quadratic twists of the L function associated with this modular form, then we know that this family can be either orthogonal or symplectic, depending on the modular form we're starting with. If we start by considering the discriminant modular form, then the family of the quadratic twists associated with the L function associated with the discriminant modular form is an even orthogonal family. So in the following, these are the three families I'm talking about. And if I say something like, for three specific families of L functions, that these are the families I'm talking about. Okay, but now the question is, what's new? I mean, everything I've said before, I mean, so far is more than known in literature. So what's original in my research? Well, basically, the idea is to add a weight, tilting the external average over the family with the weight, with the tilt, which has somehow an arithmetical mean. In particular, we want to tilt the average multiplying by the central value of the L function. So L evaluated at 1/2, and there's plenty of algebraic number theorists here with who I'm sure they agree with me if I say that this carries, I mean, this weight carries important arithmetical information. So let me write down explicitly what I mean with that. So the start is the same as in the case of Katz and Sarnak. So we take F, and we evaluated at the normalized non-trivial zeros, the imaginary part of the non-trivial zeros of the L function L, and we sum over all the non-trivial zeros. This is exactly how they started, Katz and Sarnak started, but now when we sum over the family, not only we sum over L, but also we put a weight here, L evaluated at 1/2. Now to get more freedom, we also allow an exponent to, an exponent to be here. And for a technical reason, I also need to add a technical function V here, which is just there to avoid odd moments in the unitary case. So the function V is just the absolute value squared in the unitary case and the identity function in the other. So it's not crucial. I mean, it is in the computation, but for now you can ignore it if you want. And so what's the normalization that we need? In this case, the normalization is given, of course, by the moment, the kth moment of the family we are working with. And this quantity here, which we call D, and of course, depending on the exponent K, is the quantity we want to focus on. The philosophy of this approach is basically to give more relevance, more importance to those L functions in the family which are large at the central point, okay? And for these L functions, we expect less low-lying zeros, of course, because at 1/2 they are large. And so we expect a different low-lying zeros distribution with respect to this particular weighted one-level density. Even more interesting, I hope at least, is the fact that this quantity here, D, that I've just defined, gives in some way a link, a connection between moments and one-level density. Let me explain very briefly why. So again, this quantity here is basically, a special case of such a quantity. I mean, in our case, the function G is just given by this choice. And let me consider only the unitary case for now, and assume that G is bounded. Okay, our G here, which is a function over the L functions, is bounded. Of course, I know that our G actually is not bounded, definitely, but from the Riemann-von formula, we know that this does not grow so much either. So let me assume for a while that G is bounded. So in the unitary case, from some Dararajan work, we know that the 2kth moment is basically given, comes from a specific subset of families, of L functions in the family, which are basically those which have a certain order of magnitude at the central point. In particular, this means that in such a sum, in sum like that, only those L functions which at the central point have order approximately log x to the power of k contribute, k plus or minus epsilon. So what's the meaning of that? It means that in our quantity here, we are studying a one-level density which is all focused on those L functions which are responsible for the moments, for the kth moments in the family. So it's a one-level density, but which only looks at the low line zeros distribution of the L functions which build the main term of the moments. And we know that this subset of L functions is a thin one, because it's not there are not so many L functions which contribute to the main term of the moment. So it's a one-level density, but only looking at those L functions which build the moments. That's in some way the connection that I wanted to talk about. Okay, so I'm talking a lot, but what do we expect from this quantity D here? I mean, what do we expect? What's the behavior of this quantity? Well, the idea, which is probably not surprising, is that a similar shape, as in the case of the density conjecture, and I mean, at least the same flavor should work also in this weighted case. And in particular, we expect again that this quantity D, this weighted one-level density, is again the integral of the real numbers of the test function f times again the kernel, which again does not depend on the family, but only on G, only on the symmetry type. And also there's dependence also on K. The K here is not an exponent. I'm just saying that W depends on K. And so we expect again that the one-level density also in the weighted case does not depend on the specific family, but only on the symmetry type. Of course, I didn't prove such a beautiful conjecture in full generality because this would imply the density conjecture, and I didn't prove it at all. But at least in some cases, under suitable conditions, I'm able to prove something like the star equation here, this equation here. For example, for three specific families, so for the families I mentioned before, assuming the Riemann hypothesis and the ratio conjecture, so assuming that we know how to compute the moments of ratios of L functions in the family, then if the exponent is not too large, let's say K is smaller than 4, and I'm going to maybe to say a few words about it. So under these conditions, the relation over there, the conjecture is a theorem. I'm noticing that I'm writing down, but nothing is appearing on the screen, but hopefully it will soon. Okay. In one specific, the approach here that I used is the same as Conray and Snaith. They did the same in the classical case. I basically weighted their approach under the ratio conjecture, and I proved the weighted one-level density theorem. And I just want to mention the fact that the K equals 4 is not a special case. I mean, one can do the same with K equals 5. It's just a matter of computation. So there's nothing special in the case K equals 5. In one specific case, for the probably the most natural family, the continuous family of the Riemann zeta function, if K equals 1, and if the test function is good enough, whatever it means, basically it's a condition on the Fourier transform support, the support of the Fourier transform of the test function f, then I can prove the result unconditional. So no Riemann hypothesis and no ratio conjectures are needed. And here the approach is the same given by Hughes and Brudnik in the paper. Again, they did the classical case, and by using basically the twisted second moments of the Riemann zeta function, I adapted the proof to the weighted case. Okay, so of course these two theorems, they don't prove at all I mean, not in full generality the conjecture that I wrote above, but the good aspect is that they give explicitly the kernels. So even though the first theorem, for example, holds only for K smaller than 4, actually we can speculate a little bit on what happens on the general case just by looking at the kernels that we actually have. And that's what I'm going to talk about in the next few minutes. So first of all, I'd like to mention the fact that there are relations linking, connecting the kernels with different symmetry types. For example, the unitary, okay, let's start with the orthogonal one. The orthogonal kernel with weight K, with exponent K, is going to be exactly the same as the symplectic case, the symplectic kernels, but 1K after. So what happens for an orthogonal family with exponent K is actually what happens in the symplectic case 1k after, so for k minus 1. So there's a sort of delay of the unitary, of the even orthogonal family, which is in some way chasing the symplectic family 1k after. And once we know these two, actually also the unitary case is known, because the unitary kernel is basically given by the average of the other two. So we take the symplectic kernel, we take the orthogonal kernel, we sum them, and we divide by 2. And we get the unitary one. So it's basically the average. What is fun about these two relations is that there are analogous relations also, okay, not exactly the same, of course, but the same flavor, also linking the leading coefficients of moments. If one looks back at Keating and Snaith's work in 2000, one can see the same kind of relations also linking the leading coefficients of the moments for different symmetry types. And also, these two relations allow me to just ignore two cases. I can just talk about the symplectic case from now on, because once I know that, I know everything by these two relations. So in the next 5 minutes or so, I'm going only to talk about the symplectic case. Okay, here I printed an explicit formula for the kernels that I got in the case that I was able to solve, so for k smaller than 4. I mean, they seem rather horrible, but actually they are not so bad. Okay, the expression for the kernels is probably a little bit messy, but as soon as one looks at the Fourier transform of these kernels, the Fourier transform is beautiful. Because, okay, there is a delta function, there is a characteristic function, but basically the Fourier transform of the kernel, the weighted kernel, is basically given by a polynomial, which is just a nice polynomial with certain degree depending on k. I mean, here you can see a picture of these polynomials for k smaller than 4, and these are very nice polynomials, very easy. And so by Fourier transform, by Fourier, let's say, inversion, one can get a conjectural representation, which is conjectural, of course, for k larger than 4, and a theorem instead for k smaller than 4. One can get a nice representation also for the kernel itself without Fourier transform. And it might seem a little bit complicated, but actually it's not. It's just we take this function, cosine of x over x, we consider the derivatives, and we take a linear combination with where all the coefficients are just a bunch of factorials, so they are kind of nice. So basically the kernels is conjecturally for every k integer, a linear combination of derivatives of cosine of x over x, roughly speaking. What is probably most interesting in this approach is the behavior of the kernels at 0. Why? I mean, as I mentioned before, the idea of this weighting approach, just tilting by L at the central point, is basically to give more relevance to the L functions which are larger at the central point. For these L functions, we expect less low-lying zeros, and so we expect the kernel to vanish at 0. That's that's what we expect. And so this should happen more heavily if k increases, because if k is large, if the exponent of the weight is large, I'm giving more and more relevance to these L functions, and so I expect the order of vanishing to increase more and more with k. That's exactly what happens. So if one assumes the the expression that I showed before, what I did was just getting the expansion as a power series at 0 of the kernel. The coefficients are explicit. They are quite complicated if you want, but just they can be written in terms of hypergeometric functions, so nothing bad. And what is particularly interesting is the first non-zero coefficient, which gives the order of magnitude, the order of vanishing of the kernel at 0. And this is going to be, okay, the coefficient is just, again, a bunch of factorial, and the order of vanishing is given by the power of x, which is 2k plus 2. So it increases with k. And this reflects the phenomenon that I mentioned before of, low-lying zeros that are rarer and rarer as k pieces. Okay, so just last thing I'd like to say is that this kind of weighting, which might seem a little bit artificial to some of you, I hope it doesn't, but it might be, kind of appear naturally in other contexts. For example, there is a paper by Kowalski, Saha, and Zimmerman in a very complicated setting. They consider a Siegel modular form of genus 2. And they compute basically the one-level density of the spiral functions of F with a weight for their reasons. They want to consider the one-level density with this weight, which is basically given by the absolute value square of the first Fourier coefficient of the modular form. The family is known, or at least expected, known to be an orthogonal family. They computed this weighted one-level density, so they one-level density, and they got a symplectic behavior. At first, they were surprised, but they explained this change of symmetry just by Boscherer conjecture, which is now a theorem, by the way. A few months ago, Furusawa and Morimoto should have proved it. The paper is not published yet, but should appear on GEMS quite soon, probably 2022. So what does Boscherer conjecture say? That their weight is actually proportional to L evaluated at 1/2, which is our weight. L evaluated at the central point, it's exactly our weight. And it carries arithmetical information, so it makes sense that it changes the symmetry behind the fact. Okay, so since this investigation now overlaps with ours, I'm going to tell you what happens from our perspective just in the last 30 seconds. So basically what they are doing is considering the weighted one-level density, the weighted one-level density of an orthogonal family with exponent 1. And so the kernel they should get is the orthogonal kernel with exponent 1. But from the delay principle that I showed to you before, this should be exactly the same as the symplectic case with exponent -1, k -1, so 0 in this case, which is the well-known symplectic kernels. So that's why they got a symplectic case, because they took an orthogonal family with the exponent 1 in the weight, and so they go back to the symplectic case. Okay, I just wanted to mention this because very recently many people are working on these changes of symmetry. Sugiyama this summer published a nice paper with an example of this discrepancy, this change of symmetry, and so it's kind of cool that people are working on it. I think my time is up, so I thank you all, and I'll stop here.
Actually, you have even 10 minutes if you want.
Because you told me 20 minutes at the beginning.
Maybe there was a misunderstanding, but if you want to say more, you have up to 9:30. So
okay, because I heard 20 minutes and I shortened on the talks, all the talking. Okay, yeah, I maybe could clarify a little bit about these two theorems. So something I want to focus on is the exponent k smaller than 4, because it seems like, I mean, from this statement, it seems like, maybe a k smaller than 4, everything is good, and then when k increases, the situation might change. But actually, it doesn't. So basically, in order to find the correct, an explicit expression for the kernel, one can use just a computer in order to carry the computation out. And with k smaller than 4, the computations are still doable. Also with k equals 5, I'm sure that they are, but it's just long. And since nothing seems to change in, the computation is always the same, just longer and more complicated. Basically, I just stopped at k equals 4, and I'm waiting for a good idea, for a clever idea that will hopefully have sooner or later to attack the general problem. And the reason why I need the ratio conjecture to be as an assumption is that basically this is Conrad-Yasnaya approach. This is not a new idea, but basically, if we know how to compute the moment of L prime over L in the classical case, you can get the classical one-level density. If you know how to compute L prime over L times a power of L, so times many other copies of L at the numerator, you can instead computing the one-level density weighted with the number of copies of the L functions that you can put on the numerator. That's why I need the ratio conjecture. While in the second case, for the second theorem here, the unconditional one, the situation is a little bit trickier. Well, the approach is the same as Hughes and Brodnik. So in the end, probably what I should clarify is this condition here. Basically, this comes from the following technical issues. So to prove such a theorem, one has to be able to compute the twisted second moments of the Riemann zeta function. So I consider zeta squared times a polynomial, and then the integral, the mean of this guy. And this is known thanks to a classical result due to Balasubramanian, Conray, and Heath-Brown if the polynomial is short enough. In particular, in their case, they have the absolute value square of the polynomial. So it's a quantity like p squared, zeta squared, and then they consider the integral. If the length of the polynomial is short enough, let's say shorter than t to square root of t, let's say, then the formula that they got works. Bettin, Chandy, and Radziwill, they extended to polynomial of length, let's say 1/2 plus 1/66, I think. And conjectural, this should hold until 1 minus epsilon. In my case, I actually need to control this quantity. So not the absolute value squared, but just the polynomial. And you know, by using the classical result with the length, let's say 1/2, then one can get the one level density weighted for test functions which have Fourier transform which is supported into -1, 1. This is kind of easy with the classical tools. Now, what I'm trying to do now is to enlarge a little bit the length of the polynomial that I can take in these twisted second moments, so that I also increase the support of the Fourier transform of the test function that I'm allowed to take. That's basically the picture that I mean, how the things are going to go on in the following. Okay, I think now that's all.